Hello. Today we're going to look at the subject of atomic physics, and in the next 3 videos I hope to go through quantum numbers, bonding, semiconductors, diodes and transistors. First though, let's just review what we've learned from earlier videos, and links to those videos will appear on the screen. First, we've established that an atom consists of a nucleus, very small nucleus, which is positively charged, and orbiting electrons which are negatively charged. And in order to explain why the electron doesn't simply spiral into the nucleus and annihilate, we said that the electron is not only a particle, but it is also a wave. And that wave can be represented as a wave function. And there is some formula which we've discussed in earlier videos about what represents the wave function for an electron. And we also said that the wave function squared, psi squared, is a representation of where you find the electron. So if psi squared against location looks something like this, what that means is that you're most likely to find the electron at this location, but not necessarily. It could be anywhere under that curve, but psi squared is simply a measure of the probability of finding the particle at that point. It was Schrödinger who first developed the wave equation, so-called Schrödinger wave equation, which speaks about the energy of the electron multiplied by its wave function equals h bar squared, that's the reduced Planck's constant, divided by 2m, where m is the mass of the electron, multiplied by the second differential of psi with respect to x, minus the potential, which is v, times psi. And that is in one dimension. We tend to work in one dimension to keep things simple. If it were in 3 dimensions, then you'd have to have d2 psi by dx squared, plus d2 psi by dy squared, plus d2 psi by dz squared. But we try and keep it simple. And we showed that there is a solution to this equation, which actually comes out to say that the energy of the electron is equal to R, known as the Rydberg constant, times Z squared, where Z is the number of protons in the atom, divided by N squared, where N is an integer. R is minus 13.6 electron volts, and Z is the proton number. And we showed that if we use this formula here and plot the possible energy levels in a hydrogen atom where Z will be 1 in hydrogen, then we find that if this is E equals 0, for N equals 1, the energy is minus 13.6 electron volts, because if N is 1 and Z is 1, then the energy will simply be R, and R is minus 13.6. But if N is 2, then N squared will be 4, and therefore you only get a quarter of the energy. And if N is 3, then you will only get a ninth of the energy, and so on. N is 4, you'll only get a 16th. All the way up to when N is infinity, the energy is 0, and the electron is no longer bound to the atom. This is called the binding energy, and it's negative because you have to give that electron energy to get it out of the atom. Now N is the principal quantum number, but in solving the Schrödinger equation, he found that there were 2 more quantum numbers. L, which is the angular momentum quantum number, and M, which is the magnetic quantum number. And the rules are that N can have any integral value from 1 all the way up to infinity, though in the ground state of atoms you'll find that N doesn't usually go above 8, because by then the atom is becoming unstable. L can have any value from 0 up to n minus 1. So whatever that value is, 1 less than that is the maximum value for L. And M can have any value from minus L to 0 to plus L. So those are the three quantum numbers, and they must be integers. Now in 1925, Eulenberg and Goudsmit discovered a fourth quantum number. They were observing sodium spectrum, and they expected to see a particular line corresponding to the electron jumping between energy levels in the sodium atom. What they actually observed was what's called a doublet. That is to say, two lines on either side of the line they were expecting, but very close together. Too close together for this to be two entirely separate energy levels. And they concluded that the reason for this was that the electron was either in an up state of spin or in a down state of spin. And that meant that they discovered a fourth quantum number, S, which could either be a half, plus a half, which is the up state, or minus a half, which is the down state spin. And so there are now four quantum numbers, N, L, M and S. It was Wolfgang Pauli who came up with what is now known as the Pauli exclusion principle, which is key to understanding how electrons and indeed all subatomic particles behave. He said that no two electrons could occupy the same energy state, which is the same as saying that no two electrons can have exactly the same four quantum numbers. Well, what are the allowable quantum numbers? Let's plot out various quantum options taking our four quantum numbers, N, L, M and S. When n is 1, L can only be n minus 1, which is 0. M can go from minus 0 to plus 0, in other words, it can only be 0. And S can be plus or minus a half. In other words, there are two electrons that can occupy that particular level. And then it's full, because no two electrons can have the same quantum number, according to Pauli. And where L is 0, you have what spectroscopists call the S shell. Now let's have a look and see what happens when n is 2. Now you've got two options for L. It can be 0 or 1. If L is 0, M must be 0. And once again you can have up or down electrons, which means there are two possible states for electrons here. And again, that is an S shell because L is 0. But when L is 1, M can be minus 1, 0 or plus 1, according to this rule here. And again, the electrons can in each case be in the up or down state, and that means you have 1, 2, 3 states, each of which can have 2 electrons, so that's 6 total. And that's called the P level by spectroscopists. And for n equals 2, the maximum number of electrons you can have is 2 plus 6, which equals 8. Let's do just one more. We'll take the n equals 3 level. Now the L value can be 0, 1 or 2. When it's 0, M can only be 0. And again you can have 2 electrons up or down. And that means there's a maximum of 2 in that S shell. When L is 1, rather like here, you can have minus 1 and 0 and plus 1 for the M quantum number. Each of those can have an electron up or down. And so once again you've got 6. And again, just like here, you've got the P level. When n is 2, there are 5 options for M. Minus 2, minus 1, 0, plus 1 and plus 2. And each of those 5 can have up or down electrons. And that means there's a possible 10 electrons at that level. And that is called the D level. And so when n is 3, you have a maximum of 2 plus 6 plus 10, 18 in that level. When L is 3, then the next quantum number or quantum level is called F. So the question is, how do the electrons fill up these states? Well, if we draw an energy diagram where energy is represented in this mode here, then we find that the 1s level, that's when n is 1 and L equals 0, that's the 1s level. Then the next highest energy is the 2s level, that's when n equals 2 and L equals 0, that's the 2s level. And then above that there are 3 energy levels. Those are when n equals 2 and L equals 1. And those are called the 2p orbitals. Above that is the 3s, that's when n equals 3 and L equals 0. That's 3s. Above that there are 3 orbitals when n equals 3 and L equals 1. Those are the 3p orbitals. Above that is the 3d. You remember there were 5 of those. That's when n equals 3 and L equals 2, and that's called the 3d. Now, by a strange quirk of the way it works, the 4s level, which is when n equals 4 and L equals 0, just happens to be below the 3d level in energy terms. So what does this mean? Well, electrons will always want to occupy the lowest energy level. So if you have an atom with only 1 electron in it, it will occupy that level. And that, of course, is hydrogen. If you have an atom with 2 electrons in it, that's helium, and the second electron will go in this level, but with its spin in the other direction. And now that level is complete. You can't get any more electrons in by virtue of the Pauli exclusion principle. So an atom with 3 electrons, that's lithium, will have its electron going there. And the atom with 4 electrons, that's beryllium, will have its electron there. And now that shell is complete. You can't get any more in it. The next element, that's the one with 5 electrons, is boron. And the electron goes in that energy state. Filling up energies from the lowest energy upwards is known as the Aufbau principle. But now we've got a problem. When the next electron comes along, that will be carbon, does it go here or does it go here? And that's where we have to apply Hund's rule. Hund's rule says that you always put 1 electron in each of these separate levels before you double up. So carbon, the electron will go there. Nitrogen, which is the next one, will go there. Oxygen, you'd have to start doubling up. Fluorine and neon. And neon then has a full shell. There is no more room. The next electron will have to go in the 3s level, and that's sodium. And if we look at the periodic table, we can see how these elements that we've just discussed are arranged in some kind of ordered array. For the first element, hydrogen, that goes up here. That, of course, is the 1s1. That means it's the 1s level and it's got 1 electron in it. Helium goes up here. That's 1s2. It means that it's the 1s level and it's got 2 electrons in it and its shell is complete. We're going to discover that every atom in this outside line will have a complete shell. The next atom is lithium. That's got 3 electrons, so that becomes 2s1. It, of course, has already got the inner shell. The 1s shell is complete. Then beryllium goes here. And those are the 2s electrons now filled. Over here we come to the 2p levels. And that, you'll remember, was boron, carbon, nitrogen, oxygen, fluorine, and neon. And neon is an inert gas. And the reason it's inert is that its outer electron shell is completely full. And there's no capability for any chemistry. And then we said at the next level, which starts off with 3s1, was sodium. And so you can begin to see how the periodic table takes the atoms and organises those atoms according to their electron structures. For completeness, here are all the inert gases. Under neon we have argon, then krypton, then xenon, then radon. All of those are inert gases. There's no chemistry because they all have complete outer shells. It is only when you have incomplete outer shells that's what causes the chemistry, as we'll see in just a little while.